So hello everybody, thank you to be here for the last day. So on this day we'll speak about many SAT, MaxSAT and all stuff around that. So we'll not do an introduction because the first Ruben Martins will do an introduction for all this this day, speaking about SAT, MaxSAT and a little more. Yeah, so that's all. So I will just give the parole to Ruben Martins. So Ruben Martins is an assistant research professor at Carnegie Mellon University. And so he will do this talk. Thank you.
Thank you. All right. Thank you everyone for being here. I know this is, I guess, the last day of the summer school, so everyone will be tired of all the talks, but hopefully we have amazing talks today. And today I'm going to talk to you about SAT and MaxSAT and automated reasoning. So automated reasoning has many applications, ranging from formal verification, security, planning and scheduling, and so on. And so usually how it works is that you have a real-world application, you encode it into logic, and then you use your favorite constraint solver or automated reasoning tool, and then you decode it back and you have a solution to your real-world problem, right? And you may think, okay, this was just theory, but in practice, actually, there's a lot of companies that are using this in their pipeline, like Microsoft, IBM, Intel, AWS. They all have actually formal methods teams, especially I would say nowadays, AWS is really big on this area. And this is being used every day, right? Also, there's been a huge breakthrough in SAT in the last 30 years or so. And in the mid-90s, we could only solve formulas that have a couple of thousands of variables. But nowadays, we can solve problems that have millions of variables, right? So this was a huge breakthrough. And like Evan Clark said, like this is a key technology for the 21st century. So there's the Handbook of Statistical. This is actually the second edition, which was published in 2021. And there's also the Art of Computer Programming from Donald Knuth. So he was so excited about the topic that he decided to write just his own book about it. And he said that this is a killer app because he has so many, is a solution to so many problems, right? So SAT is really, really important. So today, I'll be talking about SAT, how to solve SAT briefly, just a very high-level ideas, how to model problems into SAT, and finally, how to solve MaxSAT, which is an optimization variant of SAT. Okay, so SAT was, I guess, is an NP-complete problem, right? So we know that there's no efficient way of solving it. So you could just say, okay, so we can't solve it efficiently, we should just give up and use approximation algorithms. But in practice, actually, that's not the case. SAT can actually be solved to solve real-world problems and get you these solutions very quickly. And we often joke around, and I'll say that NP is a new P, right? So just because it's NP doesn't mean it's hard. Actually, NP is kind of easy for many cases, right? And hopefully you'll be convinced about this message and you're going to use SAT solving afterwards as well. So what is the SAT question? Given a CNF formula, does there exist an assignment to the Boolean variables that satisfies all clauses? So a bit of terminology, just in case you're not familiar with some of these terms. So a Boolean variable xi can be assigned Boolean variables 0 or 1, a literal xi or its complement not xi. Then a literal xi is satisfied if the variable is assigned to true, and its complement not xi is satisfied if its variable is assigned to false. Then a clause is a disjunction of literals, and a clause can be falsified by only one assignment, one that falsifies all the literals, and it can be satisfied with any of the other assignments. And there's a special case, which is an empty clause that is always falsified. And then a formula is a conjunction of clauses, and the formula is satisfiable if all clauses are satisfied and unsatisfiable otherwise, right? So usually formulas are defined in conjunction normal form. So this is basically a form that is conjunction of disjunctions, and is the standard input of SAT solvers. But even if your formula is not on this kind, that's no problem. You can always convert it to a equisatisfiable formula using Satan transformation, which I'm not going to talk about today, just so that you know that it's always possible. Okay, so given this SAT problem, I can ask you, okay, is this satisfiable or is this unsatisfiable? Any guesses? Yes, okay, who thinks this is satisfiable? One satisfiable. Who says this is unsatisfiable? Okay, so it's kind of hard, right? It's a big formula. So in this case, it's actually satisfiable. So if I assign x1 to 0 and x2 to 1, etc. and so forth, there's at least one literal in each clause that is green that is satisfied, right? But how can we solve this problem? Right? How can SAT solvers actually solve millions of variables of things like this, right? Okay, so I would say like this all started maybe like in the 60s. There was this algorithm called DPLL, which the idea was to find a small search tree where if you branch on the correct variables and if you're just looking for a solution, you can get lucky and you can find a solution, right? You don't need to explore this entire search space. Of course, if you're trying to prove it's unsatisfiable, then that's a different question, right? You actually need to explore the entire search space. So this was in the 60s, and the idea was very simple. It was, okay, you have a formula, I pick a variable, I branch in 0 and 1, and then I do some simplification, in this case using unit propagation, which I'll explain shortly, and then I do this again and again until I either satisfy all clauses or I explore the entire search space. Okay. So what about unit propagation? So this, I would say it's still nowadays the main technique that SAT solvers use, because this is really, really powerful, and it's a polynomial procedure. So the idea of unit propagation is if I have a clause, they have all literals assigned except for one, and they're all assigned to false. That means that in order to satisfy that clause, I need to assign the last literal to true. Otherwise, the clause will not be satisfied, right? And this is very powerful because you don't need any branching, right? This is an implied forced assignment. So if you find this unit clause and you assign that variable to true, then you can simplify the formula by removing satisfied clauses or falsified literals. You can repeat this until a fixed point or until you reach a content. And I would say 95% of the time, SAT solvers are doing this, actually. So this is really important, and this could be done even in the 60s. Okay, maybe it improves a lot in terms of data structures, but I'm not going to go over that. But at least the idea itself was there. So how does it work? A small example. Then you have this formula here, and I'll make a choice. Let's say I assign x1 to 1, to true. And then if I look at my formula, I can see here there's a clause where you have not x1 or x2. So you're missing, it's a unit clause, right? So it's a clause that only has one literal that is not assigned. So that means that x2 needs to be assigned to true. Now, if I scan the formula again, I would find another one like here that forces x3 to be assigned to true. And then here you get x4 equals to true. And now there's no more unit clauses. Therefore, you would stop, right? And in this case, not all your clauses are satisfied, so you need to continue doing search and you need to pick another variable, likely x5 or x6, and then you would be done. Okay, so how does the DPLL algorithm work? It would be quite simple. Like I said, imagine you have this formula. I would start by choosing a branching variable, let's say x2, and then I'll choose false, right? And then I'll check, do I have unit clauses? No. Okay, pick another variable and choose another value. I pick x1 to 0, and I do again. But now something interesting happens. I derive that x3 has to be true, but x3 also has to be false. So since x3 cannot be true and false at the same time, we have a conflict. So we have to backtrack. So in backtracking means I'm going to undo the last decision I just made. And this was called non-chronological backtracking back then. So you try it again. Let's say now you try the other branch, x1 equal to 1. You have a similar conflict with x3. So you backtrack again. And then in this case, I just pick x3, so the example gets shorter. And now you get a satisfying assignment. Right? So this is how it will work, even in the 60s. And surprisingly enough, I mean, you can actually solve some small formulas with this. And for certain kind of formulas, if you're very smart on how you pick the variables, this can actually be very powerful. Okay. So just we have a small break or more interactive. So here's a SAT game, originally by Oliveira Rosso. So let's pretend that we're doing the DPLL approach. So here's the SAT formula where basically you have 3CNF. So each literal is represented by its number or its negation, like -1. It represents to the not x1, for instance. This is how I guess SAT solvers have their input. And now let's try to solve this, right? Like, anyone have a guess on which variable you want to say is true or false? Pick one. Someone? Otherwise, we can't do search, right? If we don't have a decision yet. And it doesn't matter. Any Well, x1 to true. Okay, x1 to true. So okay, so we do x1 to true, and now we can see okay, some clauses got satisfied, right? And the other ones, the literal got falsified, right? So now, okay, there's no unique clauses because if there was a unique clause, there would be like an arrow pointing. So we choose another one. Any other guesses? 7. Okay, 7. All right. We took 7, and now we have some unit clauses, right? So here it says, okay, here's a unit clause. Means that in order to satisfy this clause, I need to satisfy -6, and here I need to satisfy 4, right? So those will be implied.
SAT is sharing.
Oh, is it not sharing?
No, it's not sharing.
Maybe it was just sharing the application instead of the entire screen, or not sharing at all.
No, now it's sharing.
Okay,
It's okay.
that's fine.
It was sharing the PDF.
Oh, the PDF.
Slide.
Okay. Yeah. Apologize for that. Okay, so we have here some unit clauses. So I'm just going to click on the unit clauses because those are fours. Until something happens bad. Okay. So now we got here a problem, right? So I did a bunch of unit clauses and we got a conflict. So there's a clause here that I can't satisfy. So that means that the decisions we chose were poor. They don't work out, right? So we need to backtrack, right? Luckily, I put here backtrack button. And so let's backtrack to here. Let's make like a hint maybe. And then you would continue. See if this path actually get there. All right. So if I choose another variable that my special hint button told me that this would work, you'll get there, right? But of course, if you don't have the special hint button that tells you this is a good variable to branch, we can spend here maybe the entire presentation just trying backtracking until we finish this, right? So even though unit propagation is really powerful, it's clearly not enough if you just do this DPL algorithm, right? This doesn't really scale to millions of variables. Okay. Will now this be shared or?
Shared.
Okay. Sorry. I will not change the screen anymore.
It's okay. Here for it.
All right. Okay. So what did he make actually SAT scale to millions of variables? And I would say the big breakthrough was like close to the late 90s, 2000 was conflict-driven clause learning, right? So the main idea is, okay, when I get to a conflict, can I learn why did this didn't work out? So that I can actually backtrack more precisely, and maybe I can prune more the search space, right? And turns out this is really, really efficient and works very well in practice. I would say the big weakness probably is it's really hard to parallelize. I tried myself, many people have tried it. I mean, there's a lot of papers and a lot of research on that, but it's still a very open problem. So how does it work with learning, right? So let's say I have a formula here where I'm just showing 3 clauses, and then let's pretend this is a big formula, like millions of clauses, right? And now here on the right, I'm going to show you our decision choices. So we start at level 0, where I didn't choose anything yet. And usually what we do is that we look at the formula and see, okay, if there's any clauses, then I can propagate them. In this case, I don't know here, but at least here there's not, right? So I move on. Let's say I choose x5 equals to true. Then I simplify my formula, do unit propagation, check, are there any clauses? No, move on. So I choose now x2 equal 1. And now let's say I did a lot of other decisions that are not relevant to this example. And now I'm going to choose my 7th decision. And I'm going to choose x1 equals 0. Right? And now if I look at my formula, now I do have a unit clause, x4. And this will imply that now we'll have another unit clause here, which I have x3 equals true, but here also I have x3 equals false. So I have a conflict. Right? And in the previous algorithm in VPL, we will just say, okay, I'm going to undo my last decision and I'm going to try something else. But here now we're going to analyze and try to understand, okay, why this happened, right? Like if I understand why this happened, hopefully I'll learn from it, like we all do, hopefully from our lessons, and then you can prevent that from happening in the future, right? And I'm not going to explain all the details, but I'm going to try to give you the high-level idea. You can actually see this assignment as a graph, as an implication graph. And here, basically, what I'm representing is like the nodes number is just the decision level. And if they are blue, it's kind of like they were not a choice, they were implied by unit propagation, right? So we made the choice of x5 equals 1, and we made the choice of x2 equals 1. But for instance, x4 equals 1 was a propagation because of assigning x1 equals 0 that we got that value. Right? And then you can actually, again, talking high level, but you can pretend that, or you can think about that every cut in the graph that would separate into two, where you have the conflict in one side and the rest on the other side, will actually be a potential learn clause. So one thing you can always learn is, since I made these three decisions, that means that one of them was wrong. I don't know which one, but one of them, I can't make the three decisions at the same time, right? One of them has to change. So I can say, okay, one of them has to be the opposite what I just chose. I don't know which one, but for sure one of them has to be the opposite, because I know that if I have all of this assigned x5, x2, and not x1, then this will lead to a conflict. But you can also have a different kind here, which will lead to a different clause. So here will lead to a clause that will correspond to x4, x2, and x5. And basically how this clause is built is that you basically flip the choice that you made previously, and then you can say, okay, one of these things have to happen in order not to have the conflict. That's kind of like the intuition. So why is this important fact? So you can actually definitely learn different things from a formula, and this are implied by the formula that you can always add to your original formula, and you're not going to change its satisfiability. But will also allow you to prevent this from happening in the future, right? Because if I have this clause here, for instance, then I know, okay, if I make these three choices, I immediately get a conflict without no need to search or anything like that. And not all clauses are the same. So for instance, if I would use the first clause, then I could actually backtrack to level 2, because as you saw, everything we did here didn't really matter to the conflict, right? So, and there's a procedure how you would actually do this backtracking in a more systematic way, but just pretend we will backtrack level 2. If I do this, then this clause will be unique at that level, because I still have x5 and x2 assigned to true. So this means that x1 would be implied to be value 1, right? And then I'll continue my search. But if I use the other clause, I get an extra implied y. So if I have this clause here, then this is a unique clause. So I implies x4 equals 0. And this clause here on the top, x1 or x4, would imply that x1 has to be true. So even on this very small example, you can actually see that depending on what you learn, you can actually get more information out of it, right? And SAT solvers do this. They analyze the conflict, they learn a clause. Of course, there's much more going on in the backend, but this main idea was basically what led the big difference between thousands to millions starting, right? Of course, since then, there's a lot of improvements, but I would say that this was probably the most important technique ever developed for SAT solving. Yeah, and I know it's a bit complicated, so does anyone have questions about this? Okay, so how do SAT solvers actually work out in terms of evolution, right? So this is a standard cactus plot, so that we use a lot, I guess, in the community. So the x-axis has time, the y-axis has number of solved instances, and this is using the same benchmark set, the same hardware, but just the different binaries from different decades, right? So we have a solver here from 2004. Not sure how they were able to run this there, but hopefully someone managed. And then we have different solvers, right? And at the end, we have a solver here from 2024, right? And here, you kind of can see like, so if it's higher, means that it could solve more within that time frame. So this one, for instance, solved more than 300 instances, while here we solve around 50, right? So this was 2004 or 24, right? 2003, 2007. I mean, sometimes there may be some outliers because it depends on the benchmark, but you can see that there was a huge improvement since, I mean, this was already using closed learning. So of course, it's not just closed learning, a lot of other things were happening in the meantime. But there was a huge improvement on SAT solvers. And nowadays, I would say they were very robust, very trustworthy. I mean, there was a lot of stuff that was put into making sure that results are verifiable, even when it's in SAT. not just when it's SAT, because when it's SAT is easy, right? I can just check the solution. But when it's unsat, how can you check if the solution is actually correct? So nowadays, the community solved that problem as well. And we have tools that are really robust, can solve really hard problems, right? So if you have a very hard problem to solve, try a SAT solver. You may be surprised. Okay. But how do I try a SAT solver, right? Like, how do I actually go from real world to the CNF formula, right? I mean, I only have Boolean variables. How can this work? I mean, unless your problem is not bounded, then it can't work. But if it's bounded, then there's always a way, right? So, okay. So let's pretend I'm doing an upgrade on my system, and I want to install a new package, right? When I install a new package, usually you have a message like this. Maybe there are like some dependencies that I need to install other packages in order to install this one, or maybe I have some conflicts. And at the end, I want to solve this problem, right? I want to install all packages so I can update my system. Otherwise, my system is going to be full of security vulnerabilities and other issues, right? So I have a set of packages I want to install, P1 to P4. I have some dependencies and I have some conflicts. And the first step when modeling something into SAT is that you need to define Boolean variables, right? So in this case, very simple. I have a Boolean variable PI that defines, okay, if package PI is installed, then it's true. If it's not installed, then it's false, right? But this depends, of course, on your domain and your problem. And it could be harder or simpler to create these variables, but it's always possible to do. Okay, so how do we encode this into SAT? Like I said, we start with the variables, and then we need to encode our constraints to the problem because, okay, let's say I create 4 variables. Great, I give it to SAT solver. SAT solver says, sure, I assign them to all to false. Okay, this is a solution for the SAT solver because SAT solver doesn't know anything, right? It just knows there's 4 variables. And to be honest, that actually is what SAT solver would do because by default, it assigns first to false for reasons I'm not going to go into. So we need to encode the constraints of the problem. In this case, the dependencies, the conflicts, and our goal, right? So how do we encode dependencies? Any idea? Yeah. Yeah, kind of like that. So you can say that, okay, if I'm going to install P1 implies that I'm going to have my dependencies, right? Which can be transformed with a negation of the first part in junction with the second part, right? And the same for the other ones, right? So you're basically just saying, okay, if I install this package, this is what needs to also happen. And the same you can do for conflicts, right? So if I install P1, I cannot install P4 because that's what my system does not allow me to do this. So I put everything together. Now for installing all packages, the simple way would be saying, okay, they have to be all true. Right? So if I want to install all of them, they're all unit clauses, P1 to P4. So I have my dependencies, I have my conflicts, I have my packages. I throw this to a SAT solver. What do you think is going to happen? Ideas? Either SAT or unsat, so 50-50. Okay, we'll see again. So this is the formula, right? And then I threw it, and in this case, it's actually unsat, right? So sad face, I can never upgrade my computer again. I'm doomed with my operating system from 2000. That's not really the solution we want, right? But let's look at why it's unsat, right? Again, I'm not going to show you proof. I could show you proof, but one thing that sometimes is useful is to analyze something we call an unsatisfiable subformula. So if some formula is smaller than this one, but unsatisfied by itself, right? So in this case, if I show you this, maybe it's easier now, right? So you have a clause that says not P3 or not P4, and then you're saying that I have to have P3 and P4. Okay, this doesn't work, right? I'm saying I must install P3 and P4, but I also have some sentence that says that I can't install both of them, right? And this notion of unsat cores are also actually very useful for MaxSAT, as we're going to see in the future. Okay, we can't install all packages. This is really bad, right? Because some problems may not be necessarily SAT or unsat. Maybe I want to maximize something. In this case, I want to know, okay, I can't install all of them, but how many can I install? Let's say. And actually, this is MaxSAT, which I do a lot of work myself, including my PhD. And the idea of MaxSAT is that clauses can either be soft or hard, right? A hard clause is a clause must be satisfied always. And a soft clause is like, I really wanted this to be satisfied, but if you can't, well, tough luck, you know? And then the goal is to maximize the number of satisfied soft clauses, or minimize the number of unsatisfied subclasses. Actually, solvers often look at this minimization perspective, but they're equivalent. And you can also generalize this to weighted MaxSAT, where you have weights associated to each subclass. Okay. So how do we encode this as MaxSAT, right? So what do you think are the hard constraints out of these three things? Dependencies, conflicts, and installation packages. Yeah, so dependencies are hard constraints, yeah. What about conflicts? Soft or hard? They also should be hard constraints because otherwise we will telling them, oh, ignore this conflict. We don't want them to ignore conflicts. And what about the installation packages? So yeah, so kind of like that. So it's basically the same thing as in SAT, but the difference we have is separation of constraints, right? So now we have a new formula, and the idea is maximize the number of install packages, and then optimal solution would be something like this, where, okay, I can't satisfy this one, but I can satisfy the other ones. So this is also very useful in case that, okay, I am working in a domain, there's no solution, because there's actually no feasible solution, let's say scheduling. Often we have this issue, right? So, yeah, finding scheduling with faculty sometimes can be very challenging, especially if there's many of them. How can you solve this, right? Okay, so there's many real applications, and software package availability. There's actually MaxSAT solver being used in Eclipse, or used to be. I think this still is. That manages the dependencies, kind of similar to what I showed here. Fedora used to have some SAT-based technology at some point. There was some error localization in C code, for instance. And my favorite application was for my own wedding planning. So I got married like 9 years ago, so it's a long time. But then, like, I had my tool, and I was like, okay, this is an optimization problem. Where to seat people in the different tables, right? So because they have different constraints, maybe you don't want people A to be seated with people B. Maybe you want your friends to be seated together. Maybe you want to encode other properties, right? So we encoded this into MaxSAT. We solved this. There's actually benchmarks on the MaxSAT evaluation about this, and they're actually quite challenging to solve optimally. And then we have a solution, right? And this was awesome, and it was much faster to converge. And the best thing is that if someone in the wedding came to us and said, oh, I don't like my seating arrangement, I could just tell them it was not me, it was the algorithm, you know. I had nothing to do with this. Because, for instance, we didn't actually encode distance to the to us. So some people were very far away. But that was kind of like purpose. But that was okay. I mean, not encoding the property, not having people far away. That was actually kind of random. So the MaxSAT algorithms are very effective for solving real-world problems, and should definitely try it. And similar to SAT, there was also a big revolution where, so here's just 10 years from 2010 to 2020, where you can see there's also a lot of improvements throughout the years, right? And I don't have more recent data, but maybe we can have more recent data for this year, since we have more evaluation this year on MaxSAT evaluation. Yeah, so the idea is, okay, if I have some requirements, you want to include your requirements as hard clauses and your preferences as soft clauses, right? And then MaxSAT will satisfy the hard clauses while maximizing the soft blocks. Okay, so let's see a bit more sophisticated example in terms of modeling and also in terms of how we actually solve this with using MaxSAT, right? So let's say I want to find the shortest path from S to G, and I have this grid here, and I don't want to enter the block squares. MaxSAT is not the best approach to solve this, but it does work if you want to use MaxSAT for this, of course. So again, the first step is to define your Boolean variables. So I can say, okay, each of these squares is going to have a variable, Boolean variable, and it's true if it's part of the path, or it's false if it's not part of the path. Right? Okay, that's great. And now the constraints are, I want S and G to be part of the path, so I'm going to put them as unique clauses, right? Because they must be part of the path. And then all the letters in my grids, I'm going to make them as soft clauses. Why? My idea is, and I'm going to negate them. And my idea is, I want to avoid making them to true if possible. Okay. So if I send this to MaxSAT solver will tell me, okay, I sent them all to false. Right? That was the best way solution if you don't have any other requirements. Of course, if you do that, that's not really good because there's no path. You only have S and G assigned to true, right? So yes, it's an optimal solution to that problem, but it's not really the one you want. So now you also need to enforce there's a path between S and G. And there's different ways to do this. I would say one of the most simplest ways would be, if you think about S and G, you can say, okay, since this is the starting point, this is the end point, those will only have one neighbor. And everything in the middle will have two neighbors. Because this is a path that only goes up and right and left and down, so not diagonal. Okay, how do we encode this? How do we say have exactly one neighbor? How would you do this? Let's say for S. Any ideas?
Say that if it's in the path, one of the neighbors has in the path. And if it's in the path, like one of its neighbors is in the path, the other one are not.
Yes, the notion of being in the path here is a bit more simple because if they are assigned to true, they are in the path. So we can say that one of them has to be in the path, A or B, and they both cannot be in the path. So not A or not B, but it's the same idea that you were saying. Just with using our definitions of the Boolean variables as we define them. Of course, you could define a different definition of your Boolean variables, and your problems would be slightly encoded differently. And now for G, there's actually three neighbors, K, Q, and R. And then it's kind of similar, right? You have to say at least one of them has to be in the path, and at most one of them has to be in the path. So this is the simplest way to do at most one, where you have pairwise combinations that says that at most one of them has to occur. Okay, so we have this. And now for the other ones, this was really more tricky. You have to say, let's say for E, that at most it has exactly two neighbors, right? So in this case, it has four potential neighbors, D, J, L, and F. And you want to say this is equal to 2. So this would imply to actually encode this into CNF. We imply something called a cardinality constraint. I'm not going to tell you how to do this because this is a bit more sophisticated. Actually, it's not as trivial. But there's a lot of research on this. And there's also libraries that you can use that someone already implemented this for you. So you can just call this library and say, okay, encode me this equals 2, and then transform this into CNF. Or if you actually want to improve the encodings themselves, you can also do research in that area and try to, is there a Barrett transformation that uses less auxiliary variables? Okay, if I have all that, then I have my problem. And now the purpose of this encoding is kind of like, okay, what I want to happen is, if a solution to the MaxSAT problem will be a connected path from S to G, and optimal solution will be the shortest path. So here, for instance, there's two paths. The orange path assigns 14 variables. 12 of them are soft clauses. And this green path assigns 8 variables. 6 of them are soft clauses. Right, so here you're unsatisfying 12, and here you're unsatisfying 6, for instance. Right. So now the question is like, what is the shortest path? And how to solve this. So how do MaxSAT solvers actually work? There's many actually different approaches for MaxSAT, more than SAT, because I guess there's different ways of solving an optimization problem. And here I'm actually going to talk about two kind of views, but there's even more than that. So there's a simple view would be like this lower bound search or upper bound search. So the idea would be, okay, I want to minimize the number of unsatisfied soft clauses, right? Best case scenario, I can satisfy all of them, or unsatisfy 0, right? But okay, if I can't unsatisfy 0, can I unsatisfy 1? If not, can I unsatisfy 2? If not, can I unsatisfy 3? And if eventually you stop and the answer is yes, you found the optimal solution, right? Or you can try the other way around, right? You can try to find solutions. And then let's say I already know there's a solution with 10, a shortest path with 10. Is there a shortest path with 8 or with 9 or with 7? And then you can make those questions to a SAT solver. And then the SAT solver will say yes or no. And then you can iterate and refine. Eventually you converge until you find the optimal solution. Right? So for the upper bound search, the idea is kind of like this. We're going to use the SAT solver, but we only care about two things the SAT solver gives us: a satisfying assignment and this unsatisfiable subformula if it's unsat. Right? So we don't actually care how the SAT solver works. I just care, okay, after you finish, if it was SAT, give me a model. If it was unsat, give me an unsatisfiable subformula. So we start with the question, can we unsatisfy less than K clauses? And then we can encode this into CNF and add to our formula, call a SAT solver. The SAT solver will say yes or no. Let's say yes. then we're going to change our formula in a way that now I want to ask the other question. Can we unsatisfy less than J, where J is smaller than K, right? And then I have a new formula. And eventually, if you do this into conversions, you get unsat and you prove the optimal solution. So this is just the big idea. How does this actually work out on our example? So a bit more concrete. Let's say I have my formula, and I usually start by solving the hard clauses only. So let's ignore the soft clauses. I'm only going to solve the hard clauses. Right? So the soft clauses were saying I should not use all the squares, right? So without that, SAT solver can do anything, right? So let's assume the SAT solver give you this solution that corresponds to this path. So this would correspond to assigning 10 soft clauses. And that means that you're kind of unsatisfying 10 soft clauses, right? So your cost is 10. So the question could be, okay, I know there's a solution with 10. Is there a solution that with less than 10, right? And how that would work is that we would encode this cost less than. So you can use logic to encode this, and I'm not going to show how, but this is the intuition, where I can now change my formula in a way that I'm asking the question, okay, the summation of these all variables has to be less or equal than 9 or less than 10, right? And if you have this constraint and you solve it again, you find something with 8 now, right? And now you continue iterating by refining this upper bound here on this constraint. And then eventually you get unsat. And when you get to unsat, you know that the last solution you found was actually optimal. Okay. Any questions about this approach? Yeah.
Are you using binary search at all?
That's a good question. Yeah. Why not use binary search, right? Like you're doing a linear search, maybe binary search would be much better. That's usually the most common question. People have tried, right? They can even do this is a bit better than simply having. So if let's say your optimal solution is 6, right? And I don't know how many squares we have here, but imagine I have 15. This is also 15, but imagine I have 15, right? I don't actually need to do 15 calls to the SAT solver, right? Because I'm using the last model as my improvement to the next call, right? So I actually don't know. The worst case scenario would be a linear number of calls, but the usual case scenario is much smaller than that because of the model. The main reason why we don't do binary search, or people didn't do in the past, maybe we should do it again, is because when you do binary search, 2 things can happen. It can happen SAT or unsat. So with this algorithm, only one thing can happen. SAT, 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 and then you get unsat at the end. Okay? So why is this important? When you have SAT and then you have unsat, let's say you did the binary search, let's say UB equal 3, and it was unsat. The information that you learn from the SAT solver may be not sound now if you increase the bound, right? Because the learn clauses were true with respect to that information. But does not mean that we shouldn't try this, because to be honest, like you're going to show, I'm going to talk about lower bound search, and to be honest, lower bound search is the most efficient one, and that goes unsat, 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 and there is ways to preserve information, right? But the reason why people didn't do that before was because the cost of losing information with the SAT solver was too high, therefore it didn't pay off. The potentially having just a logarithmic number of calls is linear. And in practice, you don't actually have the worst case scenario of having a linear number of calls. But maybe we should revise this idea now, because it's been a while since people have tried it. So maybe I should try it in the summer just to see if it's still valid or not, because this was true like some time ago, but maybe not. Okay, so why is this good? Like, okay, if your number of soft clauses is small, this is good. If your optimal solution is very close to unsatisfying almost all of them, this is also good. But this restriction that I did not show how to encode into logic actually can be very large, especially if you have weights. Like the single restriction can blow up your memory. So what kind of other search can we perform? Can we start with the lower bound, right? So, and to be honest, people have done this with MaxSAT, but nowadays I would say this is the most common approach, using lower bound search. So with lower bound search, the idea is to start from lower bound, I guess, where we're going to ask the question, okay, let's be optimistic. maybe I can satisfy all of them, right? And in practice, actually, another thing that happened is when you're solving a real world problem, most of the problems is almost SAT, right? Like if the problem was very, very unsat, that means then probably the solution you're going to find is also not very nice, right? Like let's say you're doing a schedule problem and at the end you find out, okay, my best solution is that I'm going to meet with 1% instead of 10. Okay, great. That's not very fulfilling, right? But if it's almost there, right? If you, let's say I want to install all packages, but I'm only going to miss one or two, right? That means if you do this kind of search, it's going to be much more efficient. So you start by saying, I'm going to satisfy all of them. If this doesn't work out, you ask the question, can I satisfy all but one? And you iterate this. This is actually a linear search as well. This is actually truly a linear search in the sense that you're going to call here k times the SAT solver, where k is the number of the optimal solution in the n-weighted case. So it's pretty bad. It's pretty bad if your optimal solution was very large. So like if your optimal solution was 1 million, yeah, this is not going to work out, right? For n-weighted, because it will provide 1 million SAT calls. But if it was 10, not that bad. Right. Okay, so what is the intuition now with the shortest path? Again, so let's say I'm going to try to solve my formula. I'm going to solve it as a whole, and it's NSAT. And now, what I'm going to look at the NSAT core of the formula. And I'm going to show it to you visually how it will look like in the grid. So the NSAT core can tell you something like, you know, in order to get from S to G, one of these two needs to be true. Otherwise, you're not going to get there. Right? So you learn that one of these has to be true. So you have this set R of variables that you're going to update. And then you're going to allow one of them to now be set to true. Because our goal was to set all of them to false, remember? But I'm going to have now this constraint cost less than. And I'm going to say, okay, I'm going to allow one of these two variables to be true. And now I'm going to call this SAT solver again. Okay. And now SAT solver may say, oh, I found another core, C and G. So one of this has to be part of the path. Right? Either this one or this one. And now I can update my set of variables I'm tracking. And I also will update the upper bound. And in some sense, I'm going to say, like, 2 of this can be true of the set, or 3 of this can be true, or 4 or 5, and so on and so forth. So this set will increase, and the lower bound will also increase. Why is this good? Because the NSAT core is often very small. So imagine I have 1 million soft clauses. If my NSAT core is only 2, I only care about those 2 clauses so far. And in practice, we can actually solve a lot of MaxSAT problems with only caring about a very small percentage of the solved clauses. Right? If I consider all solved clauses, like the upper bound search was doing, all of those variables were part of my restriction. Here, this restriction is much, much smaller because my lower bound is much, much smaller. And also my R size, also my variables is much, much smaller. So how does this actually work at the lower level, at the formula level? Because I think this is interesting to see a bit. So let's say this is a different formula. It's simpler, so we can see. So we have some hard clauses, we have some soft clauses. And I first try to solve the formula, NSAT. I ask for NSAT core. And now I want to track this soft clauses. So usually what people do is that we introduce this relaxation variables called R1 and R2. And this notion of this relaxation variables is, if I assign this R1 to true, I'm kind of allowing X1 to be false, right? Because at the end of the day, this is a SAT formula. I need to satisfy everything at the end. So a truthful solution will always be to assign R1 and R2 to true in order to basically satisfy the clause, which corresponds to unsatisfy the original clause, right? So it's a trick that people can do in order to control which clauses you allow to unsatisfy. And now I have this restriction here. And I say at most one of them can be true because I only got one NSAT core so far. So I know the solution cannot solve all of them, but I don't know if it can solve this. Now I have a new formula, right? This is a new formula and it's a SAT formula. I send this to a SAT solver. It's again NSAT. I ask for NSAT core. And now what I do is I look at the clauses that were not relaxed yet, the ones that don't have R variable. And I add the R variable if they don't have one. And then I add them to the set of variables I'm tracking, and I increase my bound. In this case, it's kind of a worst case scenario where I am tracking all soft clauses, but if the formula was very, very large, this usually tends to be a very small percentage of the entire formula, right? So the advantage of doing this is that this restriction is growing much smaller and more controlled. Right? Again, you could do actually binary search here as well. There was some research on doing that. And there was my own research in 2014. I show how you can actually preserve learned clauses across iterations, even though you're having a lot of unsat calls, and that can actually help a lot. So the same idea could be applied to the other algorithm, which I didn't actually. So I should try it out just to see if it will work or not. And then you do this until you get optimal solution. In this case, it would be 2 soft clauses. Okay. So this algorithm can be very efficient when the size of the course found in each iteration is small, and the optimal solution corresponds to satisfying most of the things, right? The downside is that you have one big constraint as well, and it didn't capture local information, right? So for instance, in the second iteration, we kind of changed our algorithm to have all these variables less or equal than 2 on the path. So remember here, go back. So this was added to my set of relaxation variables, and then I put this less or equal than 2. But we know something stronger, right? We know that each of them individually would be less or equal than 1. So you could actually change this algorithm. And to be honest, I mean, this was something I did on my own solver a few years ago. Nowadays, this is not the best approach, I would say, right? Even though it's still very competitive. So this is kind of like the evolution of just unsatisfiable based algorithms. So this is only algorithm solvers that were based on unsat cores, and there's been many of them since 2006. I would say that nowadays, most of them are using this OLL algorithm, which I'm not going to explain, but the idea is that it takes, also it uses unsat cores, I mean, all of them use unsat cores, but this one takes more local information in consideration, allows you to exploit the structure of the formal pair. And so, for instance, these ones highlighted in red are all using this OLL algorithm, including MaxSAT, which is developed here by Florent, which is a very good MaxSAT solver as well, right? So they're all like doing this. So now the question could be, okay, what's next, right? What's gonna be the next MaxSAT solver or SAT solver that's gonna change the world? I don't know, right? I think there's still a lot of research to be done. Parallelization clearly is something that is a big challenge still. But one thing that I'm also trying, because everyone is now trying, of course, is, okay, what about LLMs, right? Even though this is a SAT talk, right? And it does not seem to have much about LLMs. I was curious as well to see, like, okay, can LLMs actually generate a SAT solver or a MaxSAT solver? How well will it do? So this was a question I had in a workshop a couple of months ago. So like in April, I decided, okay, in my spare time, like 1 hour per day, I'm going to do some prompting and I'm doing some vibe coding. And it was kind of weird to me because this was the first time that I never looked at the code, right? So code 100% generated by the LLM. Even though I've written codes, so this OpenWRO is my own solver. So I've written solvers before LLMs, right? So when people are used to write their own code. But I was just curious to see how it would fare in terms of like, okay, I saw with papers, because I was also curious to read more about some more recent papers. I was giving a talk here. I was also, it's been a few years since I've been doing more research in MaxSAT. So I fed a lot of papers to LLM and did some planning of like which feature to implement. And then I gave those features, that plan, let's say, to coding agents, in this case, Codex. And then the Codex implemented that feature. And then I asked the LLM, okay, check the code to see if it was actually correct or not, or find issues. And I revised the codes, and I evaluated this on benchmarks. I did spend some time setting up pricing infrastructure, testing infrastructure with regression tests, and evaluation infrastructure. That was all done by me. Well, not by me, but not by the LLM. Let's put it that way. So because I have no idea how we could trust these results, right? So to be honest, like this code was more tested probably than my own code, right? Because I trusted less. And there were some bugs that were found, but they were all fixed by the LLM. And I submitted this to the evaluation this year, and we'll see what is going to happen, right? But this is not the best way to generate code, right? Because I didn't give actually code, I just gave papers. And some of the features are quite tricky to implement if you don't actually look at the source code. So how well do you think this worked? Terrible? You should never use LLMs for this. Okay. Any ideas? Thoughts?
It depends on how to do the prompt engineering.
So, okay, so how this worked was I gave the PDF to ChatGPT and I asked ChatGPT to give me the prompt. And then I give the prompt to Codex. So I didn't change the prompt. Except for one case where I did actually change the prompt because it was more tricky. I did the Codex, the agent.
The user interface.
No, okay, so the planning was the browser, the browser.
So it's the GUI.
The UI, yeah.
Because
And
it gives different results.
it gives you results, yeah.
Because once you pay to the API,
Yeah.
it gives you different results. To be honest.
Yeah, so this was done with like the $20 plan. Even though like last month I even had a $100 plan, they said maybe it could have been better if I would use, because for instance, with a $100 plan, there's like the pro modes for thinking. So you can have better thinking on the UI.
The prompts.
Yeah.
They give the same exercise to the GUI and the API. It gives me different two results.
Also, there's no deterministic. Every time you ask something, it will give you something slightly different. Yeah, it's in context. Yeah. So yeah, there's a lot of how you can improve this. The reason why I did the planning with the browser and the code with the agents was because I didn't want to put a lot of money on this. And if I use the planning also on the agents, you pay tokens. But to be honest, if you pay $100 per month, you could do this. All of that in the agent. Like, but this was done with just $20, so like super cheap. It took like a month. I hit my weekly limit 4 weeks in a row doing this. So it's to be honest, you should pay more if you actually want to do this. Like, yeah, we're just wrapping up as well. Okay, so how competitive was it? So here's actually like two solvers that one. So this is just for unweighted. So I didn't do weighted because weighted is more complicated. At the end of the day, I disabled a lot of features that I implemented because the code got too messy. But this is what I submitted to the competition. So this is the version I have now. And this is two solvers that won top two places like 2024. And this it's kind of like a cut spot. I only ran it for 900 seconds. So if I ran for longer, maybe it would be better. But my takeaway is like the gap is actually not that large. It was worse, right? But it was not that the gap is actually much closer than I thought. And it actually did a good job at implementing the baseline algorithm from a paper. So if you do a paper, say, implement this algorithm, it was not too bad. I mean, it was worse than the manual one because it has a lot of optimizations, the manual one, right? And there's a difference between what people say in the paper versus what you implement in the code, right? But there may be something here, right? And I did try to implement one new feature that had some small advantage. So I would not do this again in terms of like using something without looking at the code. Definitely you should audit the code and see if it's correct, right? But it can definitely help prototyping faster. And it actually does not give you wrong answers as much as one would expect. Let's put it that way, right? Even for very complicated logical algorithms. Okay, so if you want to try MaxSAT solving, here's some links. And takeaways is like, okay, SAT, we ask the question, can we satisfy all constraints, right? If you can't, you can still ask the question, okay, which constraints can I satisfy the most? And we saw some examples how to model problems into SAT and MaxSAT. And we learned a bit about the algorithms, but very high level because I don't have much time. And if you want to know more about MaxSAT, you can send me an email, or you can also read my chapter of the handbook. Here, there's also like a free PDF version. You don't need to buy the handbook if you want to know more about it as well. And then there's more references in the slides. I will share the slides as well afterwards. But thank you, and I'm open for questions. Yeah.
For the presentation, do you have a question? Yep.
So when you're doing this LLM generated solver, to which extent is that similar to existing code? Because normally it will be trained on some propos. So to which extent is it similar?
That's a good question. Like, so I did look at the code at the end, right? Trying to see like, oh, did it just like copy my codes? Because it has access to the web, right? So you could find GitHubs and you could find things. Looking at the code, I don't actually see at least a copy code, right? It does look a bit different, but I would need to. So this was done like last month. So this is very, very recent. Like, and there was no, it was not a publication. It was just more an act of interest. I was just interested to see how would this work fair. But I may want to run Moss or some other like similarity of codes between that code versus all the codes on the competition to see if it's actually copying or not. But for my initial observation was that at least it was not exactly the same from the ones I've seen.
Yeah.
Yeah, so you have the graph that shows the improvement in performance over time.
Yeah.
I was wondering if there's also patterns emerging in terms of what kind of software they're sensitive to over time. So I'm not very familiar with solving technology, but kind of my assumption is that all solvers are risk intensive.
Yes.
So I was wondering if that has changed over time. Do we have solvers now that are maybe more memory to do some sort of caching, or maybe they can be parallelized better?
Yeah, that's a good question. Like, yeah, so all the solvers are single threaded, right? So they're just CPU bounded. In terms of memory, I mean, you need memory to have your formula into memory, right? And there's like some, and every time a SAT solver learns clauses, your database will increase. And what they do is that at some point they will just delete clauses because otherwise you run out of memory, right? So you do need to have some memory, but like most of these evaluations are done with like 32 gigabytes, 64 gigabytes. So it's not like you need a huge amount of memory for this kind of problem, right? It is true that like in the past, there was a lot of studies about cache hits and misses, if you're interested in hardware, right? There was some, so for instance, how to optimize unit propagation to have less cache misses and how to build your lattice structures in a way that were more cache aware. That may have changed now with the different hardware. People don't know any recent work on that, but that could be something we should look into it. When I was in parallelization many years ago, one issue was like you're saying with cache, right? Because like LD1 cache and so on were very small. And so you would pay more because of parallelization, more cache misses. There's issues there as well. Again, those are things that people studied in the past, maybe like 10 years ago, but maybe that has changed more recently and maybe we should revise that again. Yeah.
I have a question about, I think it's slide 19.
Sure.
About clause learning. Yeah, right there. So when you got to detect a conflict, you extract a minimum, you want small clauses because they're more useful to them.
Yeah.
So you want a minimum set of literals that, as it were, covers all the conflict, all the conflicting clauses, some sense. Yeah, well, yeah. And what sort of problem is that? Is it like a min cut problem or a what?
Yeah, that's a good problem. So usually what SAT solvers do is they do in two stages actually. Like the first stage is finding a cut. And usually there's this notion of unique implication point where like there's a point in the graph while your paths will pass that is going to be closer to the conflict and usually gives you a smaller clause. But then there's also like a minimization procedure that is done afterwards and it tries to minimize the clause size. They don't actually try to spend too much time and find like the minimal clause or the best clause. I would say that SAT solvers nowadays, they're built in the sense of like, it's better to be kind of like fast and dumb than to be very clever, but to take too much time, right? So anything that takes too much time, most of time didn't pay off, right? So people tried it, but like for some families of benchmarks, maybe it's useful, but in general, being faster was just better. So the only way I saw people trying to do more like you were saying, like very strong minimization would be in parallel solvers actually, where you could say, okay, I have a thread that only does minimization. So I can still do search while other threads are trying to do other things, or simplification that can be very costly, but it would be more closer to the problems you're describing. Yeah.
Especially the fact that for this root problem, it sounds to me like it's kind of brute force. Are we checking each possible route and to find the shortest one, or is there actually it's actually pretty fast, but it just sounds brute force?
Yeah, so it's not brute force in the sense that you're not actually this is not the best way to use logic for starters, right? So if you want to solve this problem, you can do a search exploration problem and it's going to be faster. But the idea of logic is that when you put something into logic, you're encoding symbolically all this the problem, all the search space symbolically, right? So when I'm asking, give me a path, you're actually not trying to enumerate all possible paths, right? Each model, it's kind of giving you, you can map it to a path, right? But it's only giving you a few paths. So even for the improving example, so if I enumerate all possible paths, there's many more that were not enumerated in the sequence of calls, right? So here, for instance, I would have 3 calls to the SAT solver, right? And then I found 4 calls, last calls to prove that the 6 was optimal. So, but there's many more than 4 paths, right? So the idea is you're kind of like only exploring parts of the problem. And why is that? Because when I find the path of size 8, I'm saying the next path needs to be smaller than this one. So that means that you already discard all paths of size larger than 8 or equal to 8, right? So it is smarter than that in that regards, right? When you're using the lower bound approach, there's not even paths, right? So it was always in SAT, and then you get a solution. So it's kind of like the solver is saying there was no solution if you tried to find a path of size 1. There was no solution if you tried to find a path of size 2, right? And so on and so forth. And then you say, okay, here's the path of size 6. There's the solution. But so it's kind of like they're not trying to find all the paths. They're trying to ask kind of different questions there. But that's a good observation.
And maybe a follow-up question on that, because the constraint come from the domain here. And what is it if you look at the solving process? So it's working on the clause, but the clause come from geometric constraints. So you could see which are the geometric constraints that are used and what come out of that. Can you see something like on the reasoning level that this region is like more important than this other, or?
That's a good question, right? I guess your question was yeah, like how visualization on the real world could see some insights of the solving perspective, right?
Because you can map the clause to constraint here, so you could see which are the constraints that are used and the constraints that are used and the algorithms are related to regions. So
yeah, you could do that for specific problems. I guess if you have, for instance, a Sudoku problem, you could actually see like the clues getting filled and backtracking, conflicts. So there's some people have tried to do something like that. It's hard to get insights, right? Of like what is the hard part, but maybe that could be a better way, right? I don't know anyone that done something like that in a general sense, but it could be interesting.
Because the reasoning level could be interesting because it could show that what's difficult is this particular region or this kind of process, and then maybe you would have something like it's searching maybe not for a path, but it's searching for a solution somewhere.
Yeah, that could be interesting. Yeah, like I said. Usually, like since the problems are so large, right? They're not as nice as like a small example, so they're also much hard to visualize. But for a small example, but even when I'm solving like problems, let's say I'm solving a math problem, sometimes I can get insights from a smaller instance, and then I can generalize that with a larger one, right? So even having that visualization for small instances could be useful. Yeah, I think that could be very interesting.
No question? Do we have a question online or?
Questions online, no?
It seems that that's similar to reinforcement learning and especially development equation, where we have each state has their own values in which from 0 to 1, which probability in which the agent will move aside. And then there's also Q learning, in which is the probability of each action of going into each state that is state between 0 to 1. In this state, we've talked about how there is a state of moving to other movements. And by such, where there's constraint and there's neighbors, will it be too much computational effort to actually have for a grand scheme of things, for example, in the LLMs, where there's a lot of things to analyze and a lot of information to, let's say, put probabilities on, and a lot of routes to go into. Will it be possible to actually go into approach that like this, but in grand terms of, for example, for ChatGPT, maybe a critic of I don't know, social Eric Domin, and then you have to go through all of these different essays, videos, writings of his own, and then critics after him, and it's all of a scheme and possibility to follow how we see a large scale model follow the model we apply.
Yeah, and people did try sometimes to use reinforcement learning to some parts of SAT, for instance. It's possible. I would say the more closer one would be how you choose which variable to branch, right? Because that's an heuristic even SAT solvers use, right? And you potentially there are some similarities with that with reinforcement learning. There's also other approaches I did not talk in this talk about local search or stochastic approaches, where the idea would be even for SAT, right? Like one approach could actually be I start with a random full assignment, right? And then I check some clause will be unsatisfied, and then I know that I need to flip one of those literals. And then if I do this, eventually I can get lucky and I can converge to a solution. And that approach actually does work for some certain class of problems. For instance, random tree SAT, actually that's the best way to solve that problem because you don't learn anything useful. So maybe like reinforcement learning could be helpful in that regards, right? But here, unclear, yeah, how much. Yeah, so I'll look more towards that direction, I'll say. Yeah, so I guess.
A question online, how do you choose between two optimal options? 6 moves, may context imply a choice, slide 41, soft variables. Then we have a path, E, G, B, M, U, T, R. So slide 41.
Oops, sorry. Yeah, this one. Can I see the question? Sorry.
B, G.
Choose between two optimals. Yeah. So if I understand correctly, the question was like, okay, what happens if there's more than one optimal choice, right? And it's usually for MaxSAT, they don't care. They will just give you one. So if there's multiple solutions, they are optimal. Then you would need to do some sort of more like model enumeration, right? So even in SAT, if you care, let's say all solutions of the formula that are satisfiable, there are techniques there to find multiple models. So there was at one point a track in MaxSAT where we could find multiple optimal solutions. And we could extend some of our MaxSAT solver to do that. So the simplest way would be once you find the optimum, instead of stopping, you just block that solution and you ask again, give me another model, right? And you can do this. I mean, this is kind of naive, but this would be the easiest way to extend an existing solver. And that will give you multiple optimal solutions.
This afternoon, they will have a talk about that, counting, so you count how many solutions there exist. So yeah, we have a full talk on that.
The follow-up question is contextual constraints added. I think, do we need to add contextual constraints in that question that we just asked?
What is contextual constraints?
To choose.
To choose between the optimum values? No, so if you don't add anything, the solver will just give you one optimal solution. If you block that solution, it will just give you a next one of that length, but you have no control of what that solution looks like. If you want a solution to have certain properties, one thing you can do, you could use weights, for instance, like you could buy as like, okay, I would prefer all my paths to include A. So let's say I put A with a very large weight, then if there's a solution that has a shorter path with A, that will appear first, let's say. If there's no solution with A, will still be solved, right? Because it's still self-constrained, right? So with weights in MaxSAT, it will allow you to give a bit more control over the preferences.
She says thank you.
Right. Thank you for the question.
Okay. So you show that the performance over the years for MaxSAT solving is improving, so the average runtime decreasing, but are there some specific application field where there's not much progress?
It's always a bit tricky because, to be honest, so I organize the evaluation for many years, but we only get benchmarks usually. People only submit benchmarks if they manage to solve your application, right? If they didn't work, they don't use MaxSAT, right? But if it works, then you have these papers about, oh, we use this for MaxSAT, right? So often we do have more benchmarks from application domains where it did work, but there are domains where MaxSAT is not as good, for instance. Like, for instance, I also use, let's say, ELP or GROBY or integer linear programming are better for certain problems. For, let's say, if you're solving TSP problems, MaxSAT is actually not the best. So there are some graph problems, I would say that ILP will be better than MaxSAT because they do more branch and bound strategies, right? So depending on the kind of search you care for, your kind of problem, There are going to be other technologies. The good thing about that is that I often see MaxSAT, let's say, in ILP being disjoint. So there's a lot of problems that MaxSAT is very good at that ILP is very bad, and vice versa. Right? Unfortunately, I guess in the evaluation now, what often people do is that they run an ILP solver first, just in case the ILP is better, just to get a few more instances solved. But if you just run the ILP by itself, it's much worse than the MaxSAT solver.